In our last kind of topic here, we want to talk about fusion and fission. So what happens when nuclei actually combine or split apart? So nuclear fission is where a nucleus splits into two smaller nuclei. And this is different than nuclear decay because it's not just shooting off a particle, it's actually falling into two pieces. Now, in a sense, alpha decay could be seen as nuclear fission because it's breaking into a helium nucleus and other stuff. But typically what's happening with fusion is it's breaking into roughly equal size nuclei. So instead of, alpha decay is usually like you've got something with hundreds of protons and neutrons that's breaking down, that's shooting off it's hundreds of nucleons, and if it's only shooting off 6, that's not really an even split. Whereas if you've got hundreds of neutrons and you split into one, or nucleons that splits into one that's like 50 and one that's like 60, that is a much more equal split. So what you have here is you have a big nucleus. So imagine that's a bunch of nucleons, and it breaks into two smaller nuclei. So this will be called a parent nucleus, and these are called daughter nuclei. So this is a daughter nucleus, this is a daughter nucleus. In collection, they are daughter nuclei. So nuclei being the plural of nucleus. And if for whatever reason you had this one split again, you could have granddaughter nuclei of the original. So we just kind of use this, it's just a historical thing of talking about the pieces as we break down. And what's going to happen here is that energy or particles are going to be released from this. So you might also get a particle or a beta, you might get a beta particle coming off, or you might get an alpha particle coming off as well. And that's the other reason we don't usually talk about fission, because the alpha particle might just be more of a byproduct of this reaction. Anyway, those particles can fly off, they can hit other nuclei and cause things to continue to break apart. But this is the idea here, and if we have something, we know that all the particles and all the charge has to be conserved. So if you have your original thing, and let's just say it's 92, 198. I don't know what atom this is. I don't think it's probably even a state. I think it's probably not even a nucleus we'd expect. But this might decay into a one daughter nucleus with 49, and that would mean the other daughter nucleus has to have 49 minus 92 is going to be 43. And let's say this guy just has 100, and this one has 98. So we know that things have to be conserved. Or maybe you also get a beta particle, which means one of these has to be bigger, so let's call this 50. In any case, all the numbers on the bottom have to add up and be the same on both sides. All the numbers on top have to add up and be the same on both sides. Because particles can't be destroyed or created in this process, and charge can't be created or destroyed in this process. So we have to have everything kind of total up in this case. Now, like we said, this might cause a chain reaction. So we might have one decay that shoots off some beta particles that causes another decay that shoots off and causes some beta particles that shoots off and causes another decay. And you can see how this exponentially expands. And this is what we call a nuclear reaction. in particular, a nuclear fission reaction. So it's, you break apart one nucleus, the pieces of that nucleus hit other nuclei. Because nothing's really stable, that gives enough energy to break apart those nuclei. And it continues to fall apart, fall apart, fall apart. And those cause more and more and more. And that's how you get a lot of energy being released. Now, the difference between a nuclear bomb, a fission bomb, and a nuclear reactor, a fission reactor, is how quickly this occurs. So in a stable reaction, for like a power plant, it gives off those two particles, those three particles, and you catch some of them so that it only causes one other reaction. And then that gives off its pieces, but you stop one of them, and that only causes one. And then that gives off its pieces, but you stop it, and it goes one. So in other words, for every nucleus that decays, it causes one other nucleus to decay. On average. It's not going to be perfect, but on average, you're basically stopping enough particles so that you have a constant, slow, steady release of energy. The nuclear bomb is the one that looks like this, where you don't try to stop it and it just basically releases all of the energy at once. This one, the reactor releases it slowly over time. It's difficult, it's not particularly difficult to have a nucleus split into pieces and then cause more things to split. It is difficult somewhat to keep it controlled like we have here. But it's something that we've largely, I would say, mastered the ability to do that. That's why we have nuclear power plants that are using fission to create this process. Nuclear fusion, on the other hand, is where two nuclei combine to make a larger one. So you take two nuclei and you smash them together and you get out a bigger combined nuclei. This typically has to happen with tiny nuclei, so like helium, hydrogen, stuff like that, because it's really hard to get big nuclei and smash them together without them falling to pieces, because you need to have nuclei that are already stable and that are going to be more stable when they come together. This, like we said before, can also release energy or particles. Typically, this is going to be releasing energy, but it can be releasing particles. And this, like with fission, can also cause a chain reaction. So if you have a bunch of hydrogen atoms all together and you smash them together, smash a couple together with enough energy, they'll get enough energy, they'll energize particles around them to cause those energies to smash together, and this is a hydrogen bomb. It is also not terribly difficult, broadly speaking, for us to have fusion occur at a slow pace. Like, we can control the rate of fusion reactions. But at the moment, we can only control them by putting in more energy than we get out of them. So with fission, we can control them, and it's easier to control fission than it is to control fusion. With fission, we can control it in such a way that energy comes out, that more energy comes out than we're putting in to kind of slow it down. With fusion, currently with our current technology, we have to put more energy in to keep it going slow than we get back out from the reaction. So this is why we don't have fusion generators. We don't have fusion power plants, because it just doesn't work. We can't get that energy back out. I know that might be a little confusing and might be something you want to clarify or talk with me, so feel free to ask. But this is the basic idea. The main things we want you to take away are fusion, being where you break it apart, fission, where they come together. Fusion, when you fuse small atoms together, they release energy. Fission, when you break big atoms, they release energy. In both cases, that released energy can cause more reactions to occur. And then those nuclear reactions, if they happen quickly, we call them a bomb. If they happen slowly, that's what we would call a power plant. And then, like I said just now, we can control that and get energy still coming out with fission. We can't control that and still have energy come out with fusion.